Welcome to the Explainer. Today, we're jumping right into a totally fascinating real-world physics and coding mystery. We're going to basically look over the shoulder of a theoretical physicist and an AI assistant as they try to debug the actual fabric of the universe. You see, if we want to understand how reality works at a quantum level, we have to simulate it. So we'll be exploring a debugging log from a real project that's attempting to simulate space-time at its absolute most fundamental level, using something called a 4D causal set. Get ready, because this is an incredible journey where highly abstract math meets some really hard code.
Okay, let's dive into this. Picture this. You're a researcher building a simulation of space-time totally from scratch. You sprinkle points of space-time into a digital void, and you expect to see a nice, predictable wave of force, like gravity or electromagnetism, just rippling outward. But instead of a functioning universe, your simulation just collapses. The math is theoretically completely solid, but the code is spitting out absolute silence. So why would a perfectly good model of a 4D universe inexplicably break down? Well, let's find out.
Which brings us to Section 1, the Green's function trap. To figure out how a system responds to a single-point source, think of it like dropping a pebble into our digital pond. The team used mathematical tools called operators to find a Green's function, but the team fell into a massive trap. When they used a symmetrized operator, it gave this really shallow, diffusive result. It's kind of like heat slowly spreading out through a metal plate, rather than a sharp, distinct wave. But when they swapped to a retarded operator, which, by the way, is the one that should actually mimic a true wave moving forward in time, it catastrophically collapsed. Out of thousands of space-time nodes, it only returned 2 to 5 non-zero data points. I mean, it essentially died immediately upon starting. Now, to understand why this is such a tricky trap, we really need to know what a retarded propagator actually does in 4D space. Because of something called Huygens' principle, waves in 4 dimensions don't just spread out everywhere in a solid sphere. They travel strictly on the outer boundary of the future light cone. They're hollow. So initially, the AI assistant pointed out a startling possibility. What if this 2 to 5 non-zero collapse isn't a numerical failure at all? What if it's just the physics being perfectly, ruthlessly accurate, and it's showing us a highly localized light cone?
Moving on to Section 2, lining up the suspects.
Now, what's really interesting about this slide is how systematically they organized the hypotheses. To figure out if we were looking at brilliant physics or just a broken simulation, the team had to play detective. They lined up 4 main suspects before touching a single line of code. Suspect 1, is there a hidden geometry bug in the shape of the simulated box? 2, is the regularizer, which is basically a bit of math used to keep the simulation stable, accidentally dominating the actual physics? 3, is the space-time density simply way too high? Or 4, are the mathematical layer coefficients causing a catastrophic cancellation?
Time for Section 3, running the triage diagnostics.
Instead of just blindly tweaking parameters and hoping for the best, the team built a targeted Python script to act as an interrogation harness. Look at how cleanly they mapped this out. They crafted 3 specific diagnostic tests to systematically clear our lineup of innocent suspects. First, a U-histogram to answer, is the causal geometry of the spacetime actually sane? Second, a scatter plot to physically see if there is light cone propagation. And third, an eigenvalue scan to ask, is the regularizer completely dominating the data? Let's take a look at the hard evidence.
First up, 1.27%. This was the measured causal fraction. That means only about 1.27% of the points in their simulated universe could actually communicate with each other at light speed within the given time frame. And while that sounds incredibly tiny, when they ran the math, it perfectly matched the analytic expectation of the box geometry they had originally set up. The verdict? The geometry suspect is completely innocent. The space-time shape is perfectly sane.
Next up, we have this incredibly large number, 74,260. This is the ratio of the operator spectrum's smallest eigenvalue to the regularizer. In plain English, the actual physics signal in the simulation is tens of thousands of times louder than the mathematical background noise from the regularizer. This definitively proves the regularizer isn't swallowing our data either. Suspect number 2 is officially cleared of all charges.
Which leads us to Section 4, a paradigm-shifting plot twist.
At this point, you know the geometry is fine, the regularizer is fine, but when they finally fed data from the real operator matrix into the diagnostic script,
they hit a massive twist. The script returned a totally shocking revelation. When they read the output, they realized the real operator wasn't collapsing down to 5 nodes at all. When they ran a single point source, our single simulated pebble in the pond, it returned 2,566 out of 2,566 non-zeros. Literally every single node lit up. It was producing a highly diffuse response. This completely shattered the initial assumption that the wave was failing to propagate. Actually, scratch that, it was propagating absolutely everywhere.
So the crucial point is that this scatter plot confirmed exactly what we're seeing, a completely diffuse cloud of data. There was absolutely no neat, sharp, light cone ridge that you'd expect from the Huygens principle we talked about earlier. The causal structure wasn't dominating the behavior at all. And this revelation completely pivots the entire investigation. We are no longer debugging a theoretical physics issue. We are strictly looking at a matrix construction error. The matrix itself is totally compromised.
Let's nail down the culprit in Section 5, the smoking gun bug.
It's time to zoom way in from the dizzying complexities of 4D spacetime down to a basic 1D array of integers. The diagnostic revealed that the uniform diagonal value for every single one of those 2,566 nodes was exactly -32. Now think about it. In a true physics simulation with natural organic variation, you'd expect a spread of thousands of distinct, messy, floating point numbers reflecting the varying density of space-time. But instead, they found this rigid, perfectly exact, quantized number. This immediately exposes that the matrix is heavily compromised and fundamentally artificial.
Let's break down exactly why -32 is so devastating. The matrix values were expected to be a specific combination of layer offsets based on distance. The main diagonal was supposed to be a +4. Layer 1 should be a -36, layer 2 a +64, and layer 3 a -32. But the diagnostic showed that the +4 was just completely absent from the entire matrix. The matrix was purely combinatorial and utterly devoid of the expected volumetric variation. And this brilliantly illustrates how simple arithmetic pinpointed the exact bug. If you take the expected diagonal of +4 and you accidentally add the layer 1 coefficient of -36, what do you get? You get exactly -32, the exact corrupted diagonal the team found. A layer 1 neighbor coefficient was sneaking right onto the diagonal where it absolutely didn't belong.
The coding error was honestly incredibly mundane, but it resulted in catastrophic physics. The algorithm failed to exclude the node from its own causal past. To put it simply, every single node in this simulated universe was incorrectly including itself in its own layer 1 nearest neighbor list.
It's really a beautifully tragic chain of logic. Watch this. Step 1, the code computes distances to find all nearest neighbors. Step 2, naturally, the distance from a node to itself is perfectly 0. Step 3, because the distance is 0, the sorting algorithm puts that node at the very top of the list, right at index 0. Step 4, the node is immediately, incorrectly, bucketed into layer 1. A distance of 0 literally guaranteed that the node ruined its own physical data.
So the fix to save the universe? Literally a single line of code. Simply adding an explicit if g is not equal to I condition to exclude the self-index before sorting the distances. It's truly amazing to see how a single basic if statement fixes the entire spacetime matrix. It just goes to showcase how methodical, step-by-step triage conquers even the most existential dread when a complex project totally breaks down.
And with that, the bug is squashed. But, the end of this debugging session leaves us with a pretty profound realization. Now that the code actually works, the physics mystery is just beginning. What continuum Green's function should this highly non-local causal operator actually approach? The simulation is finally running, but what it's trying to tell us about the fabric of reality is a completely new frontier. I hope this deep dive really sparked your curiosity. Thank you so much for joining me, and I'll catch you on the next explainer.